Welcome to the deep dive. So today what we're going to do is we're going to try something a little different. We're going to use a stack of the latest paleontological research to essentially travel back in time.
Right. We're heading to South America, specifically to the Pleistocene Pampa of Brazil, to try and get a feel for a world that's been completely lost.
And it's so important that you, the listener, sort of discard the classic images of the Ice Age you might have.
Exactly. This isn't all about endless ice sheets and woolly mammoths. We're stepping into a much more dynamic landscape, almost tropical adjacent, but defined by these giants that belong to truly unique evolutionary lines.
Absolutely. Our focus is going to be squarely on the Brazilian megafauna, and especially these colossal ground sloths. You've got Megatherium, Eremotherium, a whole family of them.
And the goal is to reconstruct their world and understand not just what they looked like, but how they lived, what secrets are hidden in their anatomy.
And, maybe most importantly, to figure out what combination of pressures finally led to their staggering and pretty abrupt disappearance.
The whole context for this deep dive is really about time and climate. The Pleistocene, it stretches from about 2.5 million years ago right up to around 11,000 years ago.
And it was just a relentless cycle.
A relentless cycle, yeah. You had these frigid, often wet glacial periods, then warmer, drier interglacial periods, back and forth. And the end of that era, that's when we see this catastrophic loss of about 80% of all large animals worldwide, especially in the Americas.
And here is the real puzzle, the hook for this whole thing. These giants, they survived millions of years of these wild, recurring climate swings, only to vanish right when the climate was starting to stabilize and warm up. Why?
It's the central question.
And we're going to show you how modern chemistry, the stable isotopic signatures that are hidden deep inside their fossilized tooth enamel, how that acts as this perfect forensic archive.
It's incredible. It lets scientists reconstruct not just what they ate in general, but the precise climatic conditions, even the seasonal shifts during a single year of one of these animals' lives. And here's where it gets, I think, really fascinating, almost personal. We're also going to explore the surprising physical cost of just being that big.
Yeah.
We have fossil evidence showing that being mega led to rampant debilitating diseases we know very well.
Like arthritis.
Exactly. Arthritis, joint degeneration. Things that made them incredibly vulnerable, even before that final critical pressure arrived.
Okay, let's unpack this enormous subject. And maybe we should start with the very definition of a giant. What even is megafauna?
Right. So when we talk about megafauna, it's a bit of a loose term, but paleontologists, they need a clear metric. The practical definition that's generally accepted is any animal with a body mass similar to or greater than a human being.
So anything over about 45 kilograms.
Anything over 45 kilos, yeah. Basically, anything bigger than a large dog is technically megafauna.
But in the Brazilian Pleistocene, we're talking about creatures that they dwarf that definition completely.
Oh, completely. The roster of giants in South America at this time was unique to the continent. You had, of course, the giant ground sloths in this incredible variety.
Right.
Then you have the South American mastodons, which were mostly gomphothers. You had the heavy, sort of barrel-bodied toxodons.
And the predator keeping them all on their toes.
And the apex predator of the continent, the saber-toothed cat, Smilodon populator. It was an entire ecosystem just scaled up.
So let's ground this in a real place. A lot of the evidence we're talking about comes from the Pampa in the state of Rio Grande do Sul.
Mm-hmm.
If you picture Brazil today, you're probably thinking of the Amazon or the Atlantic rainforest. And that is a fundamentally different world from what the Pampa was like during the Ice Age.
It's a completely different world.
Yeah.
The Pampa biome today is ecologically pretty restricted to Brazil's southern tip. It actually has more in common with the cooler, open plains you see in Uruguay and Argentina.
So it's always been a sort of a frontier zone?
Geographically and biologically, yes. It's always functioned as this kind of biological frontier.
And a frontier that was constantly on the move because of those glacial and interglacial cycles we mentioned.
That's the key dynamic. We see clear evidence of these massive climate-driven migrations happening over deep time. During the really cold glacial periods, the cold-adapted fauna, the fauna pampeana, they would expand north, pushing deeper into Brazil.
Okay.
But then, during the warmer interglacial periods, these specialized Braziliana fauna, the ones adapted to warmer, wetter climates, they'd push back south. So the Pampa was this incredibly sensitive mixing bowl for all these different species.
And the physical evidence of this history, these colossal bones, sometimes they come to researchers in the most unexpected ways, like literally washing up on a beach.
Right.
There's a great story in the sources about a paleoceanographer, Francisco Buchmann, finding a key sloth specimen back in 2007.
Oh, this is one of those classic moments of just pure scientific serendipity.
Hmm.
Bookman was on the Concheros Beach on the Gucho Coast, just collecting samples for his own research.
He wasn't even looking for fossils.
Not at all. He parks his car, and he sees this large, oddly shaped thing among the shells and the sand. To an untrained eye, it would just look like a huge, worn-down rock or maybe a weird piece of driftwood.
But he knew what he was looking at.
Instantly, he recognized the structure. It was a preserved tibia, one of the main lower leg bones from a giant ground sloth, from the genus Glyptodon.
And the scale of it is just, it's hard to process.
It's staggering. That tibia was 60 centimeters long. You're looking at a single leg bone that confirms an animal weighing several tons was living right there on what is now the modern coastline.
So why is that particular coastline, the Gucho Coast, such a rich spot for these finds?
It really comes down to the local geology. Along that stretch of the coast, there are almost no large native rocks. It's just sand and sediment.
So anything solid stands out.
Exactly. As Buchmann himself said, if you trip over something large and solid there, you can pretty much bet it's a fossil. These things are eroding out of submerged coastal sediments. The sea churns them up, and then they just get deposited on the beach. The ocean is literally delivering the evidence to the paleontologists.
That's incredible, the ocean as a giant fossil sorter. Okay, so let's focus in on that lost world. We're talking about 26,000 years ago, the peak cold of the last glacial maximum. What was the Pampa actually like?
Well, the classic image of the Ice Age is all about the cold, and it was definitely colder than today. But the really crucial environmental factor, especially for the megafauna, was profound aridity.
It was dry, exceptionally dry.
Exceptionally dry. So the landscape wasn't necessarily a frozen wasteland, but water scarcity was what defined the entire ecosystem.
And that aridity would have had a huge knock-on effect on the vegetation.
A cascade effect, absolutely. The dense, wet tropical and subtropical forests, which need a lot of moisture, they just couldn't survive. They retracted dramatically, shrinking their range.
And their place.
In their place, you got this expansion of vast areas of open savanna and this mixed savanna-cerrado landscape.
And why was that savanna-cerrado landscape so important for the giant sloths and all their relatives?
Because that was their prime real estate, these huge grazing and browsing animals. They needed vast open spaces to find enough food to sustain their multi-ton bodies. The savanna gave them that perfect mix of grasses and hardy shrubs they needed to thrive. It was this brief, ideal window in time that was eventually destined to close.
Let's turn our attention now to the kings of this era, the giant ground sloths themselves. They're part of this superorder Xenarthra, which is a really fascinating South American group.
It is. It also includes the modern, relatively tiny tree sloths, as well as anteaters and armadillos. But their extinct cousins, they were creatures of just unbelievable diversity and scale.
I mean, their evolutionary success is just monumental.
It is. Paleontologists have identified 6 different families and an incredible 88 extinct genera of ground sloths. They first appeared about 35 million years ago and just diversified across the entire continent, adapting to almost every niche you can imagine.
Okay, to give the listener a real sense of scale, let's start with the most famous one, Megatherium americanum. The name alone, Great Beast of America, tells you a lot.
It really does. Megatherium americanum was a genuine colossus. When we say it was the size of a bull elephant, we mean it. It weighed between 4 and 5 tons.
Wow.
But unlike an elephant, its whole structure allowed it to rear up in its hind legs. When it was standing bipedally, supported by that powerful tail, it could easily reach 4 meters high. That's over 13 feet.
So just try to picture that, an animal that size browsing on branches that only a giraffe could reach today.
And then you have its close relative, Eremotherium lorelordi.
Just as big.
It rivaled Megatherium in sheer bulk, yeah, potentially up to 5 tons, and could stretch out to 6 meters long if you include its tail. It also stood about 4 meters tall. But the thing that always captures the imagination with Eremotherium are its claws.
The claws.
Its forefeet had these incredibly recurved claws that weren't just big, they could be up to 1.5 meters long.
The size of a person.
The size of a small person, yeah. These weren't delicate tools for stripping leaves. These were weapons or enormous rakes for pulling down entire tree limbs.
So supporting 5 tons of muscle and bone, that requires some pretty unique physical engineering. What were the specific adaptations they needed to manage that weight and live this kind of lifestyle?
It's a remarkable study in biomechanics. Their whole posterior structure was built for bearing weight and for leverage. The lower leg bones, the tibia and fibula, were often partially or even completely fused.
Why?
It created a single, incredibly robust pillar for transmitting all that weight to the ground. And their pelvis was wide, broad, and very deeply set.
And this all connects to that unique ability they had to stand upright, what researchers call the tripod stance.
Precisely. The fused, strong leg bones, that massive pelvis, and then that huge, heavy tail, which is basically pure muscle, formed the 3 points of stability. This tripod stance was absolutely vital for them.
It's what let them become high-level browsers.
Exactly. It let them raise their enormous bodies up onto their hindquarters, turning them into these mobile stepladders to reach high vegetation. They could just rip entire sections of foliage right off the trees.
And we also noted that their feet didn't work like other big mammals. They weren't walking flat-footed.
No, they couldn't have. It would have been impossible with the size and the curve of those huge claws. If they put their paws down flat, the claws would have been digging into the ground or getting caught on everything.
So how did they walk?
They walked on the sides of their feet. They would roll their massive weight over the edge of their paws. It must have resulted in this very characteristic kind of lumbering gait, which is a sharp contrast to their immense power when they were standing still.
And when we look at the fossils, even though they were so huge, their teeth suggest they were pretty picky eaters. They weren't just giant leaf vacuums.
That's a really key detail, especially for Megatherium. It's a highly selective feeder. Fossil analysis suggests it had a U-shaped prehensile upper lip.
A prehensile lip?
Yeah, much more advanced than modern herbivores. It let them precisely manipulate vegetation to grasp and pull specific leaves or softer shoots, choosing the best parts of the plant. Their teeth were made for cutting and shearing, not for the heavy grinding you'd need for tough, fibrous grasses. They were gourmet giants in a way.
Okay, so this brings us to one of the most controversial and frankly cool debates in sloth paleontology. The idea that they weren't strictly vegetarian.
Right.
Could the giant sloth, this herbivore, have also been a scavenger, a complementary carnivore?
This hypothesis, it stirs up a lot of debate. Because chemically, from isotope studies, they look like herbivores.
Yeah.
But the behavioral evidence for them being opportunistic scavengers it's compelling. The sheer scale of Megatherium's body and its claws suggests it could get to resources that were off limits to everyone else.
And the most compelling evidence for this involves another massive creature from the Pampa.
The Glyptodon. The Glyptodon. I mean, just picture a giant armored armadillo. Think of a Volkswagen Beetle covered in thick, rigid, impenetrable bone armor, weighing over 700 kilograms, sometimes up to 2 or 3 tons.
It was basically a walking tank.
It was immune to predation, but we have found Glyptodon fossils that appear to have been killed and then flipped onto their backs.
Exposing the only vulnerable spot, the soft underbelly.
Exactly. Now, the kinetic force and the leverage you would need to flip over a 3-ton rigid shell would be immense. And of all the megafauna around, only Megatherium, with its massive tripod-supported leverage and its powerful claws, realistically had the strength to do it.
So it might not have been a primary hunter, but it wasn't passing up a free meal.
That's the idea. The prevailing view is still that they were primary herbivores. But this evidence strongly suggests a complementary diet. Maybe they drove off other predators or flipped over an already dead Glyptodon to get at the good stuff inside. It just fundamentally changes how we think of these so-called sloths.
It really was a high-stakes ecosystem, and that's reinforced by the other giants that were roaming around. Tell us a bit about the Toxodon platensis.
The Toxodon was a huge part of that landscape, a very hefty herbivore, often compared in size and bulk to a rhino or a hippo. It weighed somewhere between 1,300 and 2,000 kilograms.
Wow.
And it's often found near water sources, which has led to speculation that it might have been semi-aquatic, a bit like a hippo today, maybe using the water for refuge or to feed on plants. Its teeth were adapted for continuous wear, so it was eating some pretty coarse, abrasive stuff.
And then finally, the animal that kept them all on edge, the ultimate apex predator.
That would be the magnificent Smilodon populator, the South American saber-toothed cat. At a potential weight of 400 kilograms, it was arguably the most powerful cat that ever lived.
And it was hunting these thick-skinned giants.
Exactly. It was hunting the ground sloths, the Macrauchenia. And the key to its strategy was those enormous upper canines, up to 28 centimeters long. They weren't for wrestling. They were for making these highly specific surgical cuts to the throat to cause rapid blood loss. The fact that these massive cats existed confirms the sheer danger and power of the megafauna they were hunting.
What's so exciting is that we don't just have to guess about their lifestyles based on their bones anymore. Modern science lets us read the environment and diet from the inside out, using their teeth as these perfect little archives.
It's amazing.
So let's dive into the stable isotope analysis.
This is where the chemistry of the Earth basically becomes our time machine. Stable isotope analysis uses the ratio between the naturally occurring light and heavy forms, isotopes of elements like carbon and oxygen.
And these get into the animal's body through food and water.
Right. And because tooth enamel is so durable and it's biologically inert once it forms, it just locks in the precise chemical signature of the environment from the time that enamel was developing. It's a perfect snapshot.
Okay, so let's start with diet and carbon isotopes. How do scientists use the ratio of, say, carbon-12 and carbon-13 to figure out if a giant sloth was eating trees or grass?
It's all based on how different plants do photosynthesis. There are two main pathways, C3 and C4. C3 plants, and this includes pretty much all trees, shrubs, and cool climate grasses, they use a process that tends to exclude the heavier carbon-13 isotope. So they have a lower ratio of heavy carbon.
And C4 plants are the opposite.
C4 plants, which are mostly grasses that thrive in warmer, sunnier, often drier places, use a pathway that's less selective.
Yeah.
So they end up with a much higher proportion of the heavier carbon-13. By analyzing the ratio in the herbivore's tooth, you can calculate the percentage of C3 versus C4 plants that animal was eating.
And this was used on the Megafauna from the Brazilian Pampa. So what did the analysis of those teeth actually show?
Well, researchers like Renato Pereira Lopes, they analyzed camelids from the region, both extinct and ancestral species, because they're excellent environmental proxies. And they found a very clear and strong preference among these camelids for C3 plants.
So cooler climate vegetation.
Right. It confirms that the Pampa environment, even at the coldest peaks of the Ice Age, was mostly sustaining vegetation from cooler, temperate climates. Those warm C4 grasses didn't completely take over, which is something some climate models had initially suggested.
Okay, so carbon tells us about the food. But to understand the climate itself, especially how dry or wet it was, we look at oxygen isotopes.
Oxygen isotopes are the key indicator for aridity, and this works particularly well with large animals adapted to dry conditions like camelids because they're known to get most of their water from the plants they eat, not from drinking directly.
So how does the ratio of the oxygen isotopes change based on how dry it is?
It's all about evaporation. In hot, arid environments, water molecules with the lighter oxygen-16 isotope, they evaporate much more easily and quickly. That process leaves the remaining surface water and the water inside the plants increasingly enriched in the heavier oxygen-18.
So a high oxygen-18 ratio in the tooth enamel means a very dry environment.
Exactly. And the analysis of those Pampa camelid fossils was crystal clear. The high oxygen isotopic ratios they found proved that the environment around 26,000 years ago, at the peak of the last glacial maximum, was exceptionally dry.
And that's what drove the retreat of the forests and the expansion of the savanna.
Precisely. These fossils are quite literally archives of environmental conditions.
And I understand that paleontologists are now pushing this analysis even further, trying to get beyond just a general snapshot and achieve this hyper-focused time resolution.
This is the real cutting edge of the research. The work of Mario Dantas and his team on giant sloths is a great example. Instead of analyzing the whole tooth, they're now segmenting the fossilized dental material into these tiny portions that correspond to annual growth rings.
So it's like reading tree rings, but inside a sloth's tooth.
That's a perfect analogy.
Yeah.
By analyzing each tiny segment separately, they can pinpoint detailed climatic and dietary shifts that happen throughout a single Pleistocene year. They can see if the dry season forced the animal to switch to tougher food sources, or how the isotopic ratio changed during a particularly wet or dry year.
It's turning a static picture of the Ice Age into an ecological film strip.
It really is. It shows us the seasonal pressures and the adaptive strategies of these giants in incredible detail.
That precision is just mind-boggling. Now, let's pivot from the world outside these giants to the immense biological cost of just being that massive, carrying 4 or 5 tons around for a lifetime. It must have put extraordinary stress on their bodies.
Oh, it truly did. The physical demands of that tripod stance, of standing bipedally, of just dragging that massive bulk across the landscape, it required unbelievable musculoskeletal strength, but it came at a severe chronic cost.
And the fossil evidence shows that these megafauna were highly susceptible to inflammatory diseases, just like us.
Very much so. We're talking about arthritis and pseudogout. The evidence for severe paleopathology is stark. Researchers found Eremotherium specimens from Bahia that show wear and remodeling characteristic of chronic joint disease, specifically arthritis and spondylitis, which is an inflammatory condition of the spine.
So these multi-ton giants were constantly in pain.
One lumbar vertebra even had this calcified buildup that's incredibly similar to what we diagnose in humans as pseudogout, which is caused by calcium crystal deposits. They were navigating a high-stakes, predatory world while suffering from chronic, debilitating inflammation.
And this wasn't just a one-off thing.
Not at all. Of the 9 species of giant sloths we know lived in Brazil during the Pleistocene, pathologists have already officially diagnosed 5 of them with this chronic joint issue. It wasn't an isolated incident. It was an epidemic of being mega-bodied.
And it wasn't just the chronic wear and tear either. They also suffered from major, abrupt injuries that would have drastically impacted their survival.
Yes, the Toxodon fossils provide vivid evidence of that. Researchers found specimens with signs of a major traumatic injury, a ruptured tendon in the metacarpovavi bone, which is basically the knuckle and upper part of our ring finger.
And for an animal that size, a ruptured tendon that's a huge problem.
For a 1,500-kilogram animal in the wild, it's essentially a death sentence in slow motion. That kind of rupture would be caused by an extremely sudden, strenuous movement like fighting, or maybe the immense strain of trying to flee a saber-toothed cat.
It would compromise its ability to move, to bear weight.
Instantly, making it almost impossible to find food or escape predators. Sustaining that kind of weight without any modern medicine, being mega, cost their joints and their survival a very high price. It just made them that much more vulnerable when the environment started to unravel.
So we've set the scene. A continent of powerful, specialized giants that were nonetheless struggling under the weight of their own biology. Now we have to turn to the final, chilling chapter, the Great Disappearance.
The Quaternary Extinction event.
Yeah. The largest pulse of megafauna loss worldwide happened between the end of the Pleistocene and the dawn of the Holocene, around 11,000 years ago.
And the scale of it is worth repeating. In a very short geological time frame, over 80% of all terrestrial animals weighing over a ton just vanished. And the extinction was remarkably selective. It targeted the giants.
Right, while smaller animals and plants mostly persisted. So for the last century, this extinction has been debated, really revolving around 2 main explanations. Let's start with Hypothesis 1. Climate change was the main driver.
The climate change hypothesis argues that massive climatic shifts were the final straw. We talked about the glaciation bringing aridity, but the extinction pulse actually correlates most strongly with the post-glacial period, the rapid shift to Holocene warming.
So the giants couldn't handle the thaw.
That's the idea. The rapid global warming led to massive changes in local biomes. In Brazil, the rise in temperature and humidity allowed dense, closed tropical forests to rapidly re-expand across areas that had been open savanna.
And that destroyed the megafauna's primary habitat.
Exactly. Dense forests are terrible habitats for massive grazing herbivores. The density of the vegetation, the lack of open ground, it meant their optimal habitat just shrank away, fragmenting their populations and basically starving them out.
Okay, that makes sense. But as we noted earlier, the sloths survived multiple, equally severe climate crises over millions of years.
That's the problem.
Why did this climate shift prove fatal? And that leads us directly to Hypothesis 2, the human overkill theory.
The human overkill theory posits that the arrival of modern humans, with their advanced hunting tools and strategies, was the critical new variable. It was the final blow that tipped these already stressed populations over the edge.
And the timing is what makes this theory so powerful, isn't it?
The correlation is just. It's globally consistent. You look at Australia. Megafauna extinction happens right around the time of human arrival, about 46,000 years ago. In North America, the main wave hits around 13,000 years ago, almost immediately after humans get established.
And then South America follows shortly after.
Just 500 to 1,000 years later, perfectly coinciding with human expansion across the continent. This near-global synchronicity of extinction with human arrival often happens without a clear correlation to a major local climate shift at that exact moment.
And their whole life strategy made the megafauna uniquely vulnerable to human hunting.
They were quintessential K strategists. They lived long lives, they matured slowly, and they had very low reproductive rates. A giant ground sloth might only have 1 or 2 offspring every few years.
Which means if hunters are removing even a small number of breeding adults each year, the population just can't bounce back.
It can't replace itself.
Yeah.
That small, sustained hunting pressure, especially when combined with the stress of a changing climate, just becomes an extinction throttle.
So what's the hard evidence that humans were actually hunting these giants in South America?
Oh, we have concrete evidence of interaction.
Yeah.
Zoo archaeological finds show that South American hunters had a clear preference for large, migratory megamammals like giant sloths and glyptodons. They just yielded a massive caloric return.
So we have fossils with tool marks.
In Uruguay, yes. Scientists have identified over 1,000 megafauna fossils, including giant sloths, with distinct arrow marks and processing cuts. And in Rio Grande do Sul, they found empty Glyptodon carapaces, suggesting humans might have even used the shells themselves, maybe as shelters.
But the sources also note that this picture isn't uniform across the entire continent, right?
Yeah.
Especially in Brazil's interior.
That's a crucial nuance, yeah.
Huh.
In many famous Brazilian archaeological sites, especially ones with a lot of rock art like Serra da Capivara, you see depictions of megafauna, but they're not always shown being hunted.
So the impact might have been more indirect in some places.
It suggests that in some areas, the initial human impact might have been through competition for resources or maybe using fire to alter the landscape rather than direct, dedicated hunting of the biggest animals. But when you look at the whole continental record, that timeline correlation still makes the human factor paramount.
So let's bring this back to the sloths. Why did they survive countless climate extremes over 35 million years, only to collapse during this final transition?
The sloth study, I think, provides one of the strongest arguments against climate being the sole cause.
Right.
As one researcher put it, and I love this quote, "Nenhuma crisis climatica anterior as a liminis." No previous climate crisis wiped them out.
Wow.
Their abrupt decline around 15,000 years ago coincides perfectly with human expansion, a pressure that was completely novel and overwhelming for a slow-reproducing K strategist.
So it was the 1-2 punch. Climate change created the vulnerability.
And humans provided the fatal sustained pressure.
Exactly.
The climate changed the rules of the game, it shrank their habitat, and at the exact same time, a new intelligent predator showed up and exploited their biological vulnerabilities.
And this also explains which sloths survived.
It does. The modern, tiny, slow-moving tree sloths. They likely survived because their small size and their adaptation to the dense, wet forest canopy gave them a refuge. They became inaccessible. The giant ground sloths couldn't use that refuge, so they vanished, while their smaller, arboreal cousins adapted to a niche that was just too difficult or too low yield for human hunters to bother with.
This whole extinction event, though, it left a legacy beyond just disappearance. The sources highlight that the surviving megafauna also suffered this catastrophic loss of their historic geographic range.
This is a critical point that connects the past to our present. Extinction isn't just about total eradication, it's also about massive contraction. You look at animals that survive like lions, which once roamed across North America, Europe, Asia, and Africa.
And now they're just in isolated pockets.
Exactly. Restricted largely due to ongoing human pressure and habitat fragmentation that really began in the Pleistocene, the human impact is both terminal extinction and chronic, this restriction of range.
The loss of evolutionary function in the Brazilian Cerrado today is a testament to that.
It is. The largest land mammal left in the Brazilian Cerrado is the tapir, which weighs maybe 320 kilograms. That's a massive evolutionary drop from the 7-ton Glyptodons and 5-ton sloths that defined that landscape 15,000 years ago. The small, slow, modern sloth is the last remnant of a lineage that once commanded an entire continent. It just highlights the rapid, profound loss of diversity.
We started this deep dive on a Brazilian beach with the improbable discovery of a 60-centimeter giant sloth tibia. We used the chemistry locked inside their teeth to reconstruct their world, understanding their diets and the profound dryness of the last glacial maximum.
We saw that despite their impressive scale, these creatures paid a devastating biological price for being mega, suffering from chronic joint failure and acute injury.
And finally, we synthesized the evidence pointing toward that dual catastrophe: climate change restructuring the ecosystem and human expansion providing the lethal sustained pressure that ended this incredible age of giants in the Americas.
The saga of the giant ground sloths is 35 million years of extraordinary resilience, and it was concluded by a moment of immense fragility that permanently reshaped the planet.
It's a sobering story.
It is. The researchers who study these remains, they describe them not just as fossilized bones, but as files of environmental conditions and flashes of moments in history. And they show us a very sobering truth. The creatures perfectly adapted to survive millions of years of natural climate chaos were ultimately unable to adapt to the new, overwhelming pressure from a single intelligent species.
Which leaves a pretty profound final thought.
I think so. The question remains, if our prehistoric ancestors, armed with nothing more than rudimentary tools, could so profoundly reshape the planet and eliminate creatures the size of elephants, what does the study of their extinction teach you about our responsibility today, armed with the power we currently wield? The lessons of the Pleistocene aren't just history. They are a critical warning.
A truly profound perspective. Thank you for joining us on this deep dive.